Um, hey everybody. So just to give everybody a heads up in terms of where we are in the class, this is the second to last week of class. So we're going to start presenting presentations next week. So we'll be starting off on Monday with the CHE 508 students. And then we're going to continue along on Wednesday, Friday, and the following final exam date for last presentation. So I posted an announcement earlier to the 408 students about some other things to think about moving forward. So please let me know if there are any questions about that. So today and this week, we're going to be finishing up a few last concepts, mostly related to surface tension and surface properties. So one thing I think that is useful to talk about now is this relation. We're starting to develop some relationships between this idea of there being a surface, a pressure with regards to curved surfaces. And this sort of relates this area related to surface tension to colloids. Because if you remember, the Young-Laplace equation gives us a relationship between a pressure drop and the surface tension, so a pressure difference. So if we are thinking about the pressure versus atmospheric, so if we have a droplet of some kind with radius r, and out here is atmospheric pressure, let's call that P naught. We have a pressure here, delta P, which is equal for a spherical droplet 2 times the surface tension over the radius. So on Friday, we saw that this can have enormous consequences in terms of pressure. So Friday, we talked about nanomaterials where the radius is going to be on the order of 10 to the minus 9 meters. So that results in pressures in the orders of, on the order of 100 or more. Let's say more like 1,000 for 10, if it's really 10 to the minus 9. 1,000 atmospheres or so. Okay, so that means that a lot of weird stuff can happen when we have nanoscale systems. Okay, so let's think about some other things that we have been talking about. So we brought up a dimensionless group called the Marangoni number. So this has to do, if you remember, the Marangoni number has to do with the surface tension driven flow force. So if we think about this in terms of scaling, this would be, so how we define this was gamma, remember we define it as gamma surface tension over characteristic length. No, sorry. Wait, I can't remember how we defined it. Let me look back really quickly to remember how we defined it this year. So Marangoni number, we defined as gamma delta T d over mu k, or kappa. So the idea here is that we are comparing two different effects, and this we can call this Marangoni effect, which is a surface tension driven flow, or the Marangoni force, against the effects of curvature that we have. It's another way of stating this. So there are other things that we can compare to get some other dimensionless groups that we can consider to get some insight. So we think about oftentimes droplets moving, right? So oftentimes nowadays we're thinking a lot in terms of COVID, talking about projected aerosol droplets, right? To get an idea of how do these droplets break up, and how big are they? How do they evaporate? So let's think about that that question. Let's say in the case of aerosol, but these can apply to other systems too. Okay, so we can think about just one droplet, again, with radius r. And it's moving. So suppose it has some velocity, let's say u. So there's a couple different effects here. So we have this velocity that's going to cause some inertial force that can cause it to break it up. Inertia can break this up. But we also have this effect of the curvature. So in the case of the curvature aspect, there is going to be an energetic penalty for breaking this up. The pressure, if you're to break this up, say, into two smaller droplets, that needs to be balanced out by this effective pressure increase, right? So we know that the pressure related to curvature scales is 1 over r. So we're going to have a big pressure increase that needs to apply for that to happen. So these are going to balance. You can think about how this inertia can, or this force that's dictated by inertia can provide this pressure. So that's going to have to balance out. So we'll see how that works in a second. So we can, just like we have a dimensionless group for inertia and various other things, like for example, you know that the Reynolds number is a comparison between the inertial force and viscosity. In this case, we can make a dimensionless group. There's a dimensionless group that exists if we want to compare the inertial contribution versus this curvature. So this is known as the Weber number. No, this is written as WE. And it'll have some similarity to Reynolds number. So it'll rho, the magnitude of the velocity, times the characteristic length, A, over the surface tension. Okay, so that's one relationship we have. So we have a scaling relationship that can compare these two effects that we have here. Okay, so what about the effect of pressure? So there are other things that we can think about in terms of the stability of a smaller droplet. Just a second. So let's consider a small droplet in equilibrium with some liquid. So we can think of a container that contains some liquid. And we have some vapor up here because of vapor-liquid equilibrium. It'll have some vapor pressure, we'll call P naught. And let's imagine there's just one droplet up here that's very, very close to the surface. So again, it's liquid. It has some radius r. And we know that delta P equals 2 times surface tension over r. So assuming our system is isothermal, meaning that we're not changing the temperature anywhere, which is oftentimes a reasonable assumption, we can say that this change in liquid, or sorry, change in Gibbs energy for forming this droplet is related to P naught to P naught plus delta P, where delta P is our Laplace pressure, times the molar volume of the liquid dP. So this comes from just the thermodynamic relationship that delta G is that you learned in your thermodynamic class. Right, let's put a note here. This here is molar volume. Okay. So if we have this VL delta P, or this VL delta P term can be described as, or we can substitute this in, sorry, everybody blanked out for a second. We can solve this, and this will just be VL delta P if you simplify it. So this will be 2 times the molar volume of our liquid times the surface tension over R. Okay, so that would be the change in the liquid Gibbs energy. So we also know that if we're forming that droplet out of vapor, there will also be a Gibbs energy associated with that. And this would be V volume of the vapor dP. And we can assume in this case, the volume of the vapor can be described as ideal gas law for simplification. So we can say this is RT dP over P. Right? So remember ideal gas law, when we're using molar volumes, will be PV equals RT. Okay, so that's direct substitution there. So at equilibrium, the changes in Gibbs energy for the liquid and vapor will be equivalent. chat windows open. Okay. And we can solve. And we will get that 2 VL times the surface tension over the radius of our droplet equals RT log P over P naught. Where we're saying this P is our P naught plus delta P. And remember, this P, delta P, is the Laplace pressure. Okay, so this equation here is known as the Kelvin equation. And this allows us to relate the droplet of a liquid, or it actually can also work for a vapor bubble, the relationship between the vapor pressure and its size. So let's work out what this can look like in terms of this. So this relates the vapor pressure change with droplet radius r. So let's see what the consequences of this look like. So a couple things that we can think about here. First is for a liquid drop. So suppose we have a droplet here that's in vapor. So since for this droplet, R is greater than 0, this pressure that we have in our system is going to be greater than the P naught, where P naught is the vapor pressure for the bulk liquid. Is higher for the droplet. So the other thing that we can consider here is what about for a bubble in a liquid? So in this case, we have a vapor bubble and the surrounding medium is liquid. So the way that we treat this is that this is a droplet with a negative radius. So another way to think about this in terms of it is a liquid droplet with negative curvature. Right, it's the inverse of a droplet. So what we find here is that the pressure, the vapor pressure in the bubble would be less than the equilibrium vapor pressure for a bulk system. Okay, so let's get a look at what this means. What is this magnitude here? So you can do these calculations yourself. It's not very hard. So let's take a few different cases of water droplets sizes. And let's do this for water at 25 degrees Celsius. And remember, surface tension here is 72.8 millinewton per meter. So let's scale this down from, say, a micron size droplet, 100 nanometers, and 1 nanometer. And let's look at this P over P naught. So that would be the ratio of the vapor pressure versus the for the droplet versus the vapor pressure for a bulk system. So for 1 micron, this is 1.001. So we get essentially an increase in vapor pressure of 0.1%, so sort of small. And as we go down in size, we'll see that it's 1.018. So we got about 2% increase in vapor pressure here. And for 1 nanometers, this will be 2.94. So very large increase in vapor pressure for small droplets, very small droplets, so nanometer size droplet. So we can do the same for bubble, and you'll see it follows the same trend. The math will be the same. So for 1 micron bubble, this would be 0.99. And for 1 nanometer bubble, this will be 0.34. So let's think about what this means for a couple different things, aspects. So first off, small droplets are not kinetically stable, or less kinetically stable, let's say. So if you have a very small liquid droplet, like a 1 nanometer droplet, it's going to evaporate quickly because it has a vapor pressure that's 3 times greater than a bulk water would be. So they'll evaporate more quickly. As R becomes smaller. So when we think about things like aerosols, for example, this works a couple different ways. One way to deliver medication, for example, so if anyone, so for people with like pulmonary diseases or asthma, oftentimes people will deliver liquid medications through a nebulizer, which makes very small droplets, and those are able to come in to be inhaled as a liquid delivery system. But it should be designed in a way such that you have droplets that can maximize the, deliver as a liquid. So there's a limit to how small you can get without these basically evaporating instantaneously or very too quickly. So you can also see for the case of the bubbles, the vapor pressure surrounding very small bubbles is smaller. So one that affects things related to mass transfer. So if you're interested, for example, of using a gas bubble system to move something from a liquid phase to a gas phase, such as in a chemical process where you're trying to extract something through scrubbing, this has an effect. So small bubbles. Lower vapor pressure. So the vapor in there has a lower concentration, essentially. So this has some other effects when you go to non-liquid systems that are pretty well known, and this applies to liquids as well. So we can apply this to a solid system. We can apply this to solids too. In this case, we don't use pressure because that's not very meaningful for solids. Oops, that should be R. But we can use the activity instead, where A would be the activity in the liquid, or sorry, in the solid sphere with radius r, and A naught would be the bulk activity. So remember, activity is related sort of to fugacity and activity coefficient. But if we have an ideal solute, this simplifies because the activity is related to the concentration or is proportional to it. So if it's an ideal solute, this would be RT log X over X naught, or that's simply just the mole fraction of some species. Of some dissolved material. So what does that mean? So if we have two solid particles, and this actually does apply to liquids as well, with different radius. We have x1 here, that's great. We can say because R1 is less than R2, we know that at equilibrium, x1 is going to be greater than x2. So that means that if they have the same concentration, so say if they're pure species, for example, we are going to have this results in net diffusion from small particles to large particles. So the consequence of this is the small particles disappear, sort of like what we were saying before for the case of small droplets. And are consumed by the large particles. So this phenomenon is known as Ostwald ripening. This was noted by Friedrich Ostwald in solids in the late 1800s. So this applies to solids. It also applies to liquids like emulsions. So for example, if you have an emulsion system and you have a wide polydispersity in emulsion droplet size, the small ones will basically go and feed the larger ones, and that can give you uncontrolled growth, and it could break apart your emulsion, for example. So this is important when we're trying to understand the stability of colloids too, in a different way. So this has to do with the size stability of colloids. So again, a way to summarize this is large particles grow at expense of small particles which are less stable. Okay, so that's an important effect here. So let's start thinking about some other effects that we can think about. So specifically, we just discussed this Weber number. So let's revisit this. So moving back, just to remind you, Weber number back here, where is related to rho mu squared A over the surface tension. Okay, so can we estimate droplet size of a liquid jet? So oftentimes what happens when you have the beginning stage of some flow or droplet formation, you start with a jet and it breaks up into little droplets spontaneously. So can we estimate the droplet size of a liquid jet? Let me phrase this a little bit different. Droplet size formed by breakup of a liquid jet. With velocity of u. So to a first approximation, we can say that the curvature force should balance out the inertial force. And that should give us a good idea what a droplet size would be with some particular surface tension. So again, this will be an estimate. So that means that this ratio would be the Weber number around 1. So density u squared. And for A, characteristic length, we can use the ending radius of our particle over surface tension. So we can rearrange this and say that our droplet radius, our drop, should be about surface tension over density times the velocity squared. Okay, so this means that when we are trying to understand, for example, when a person sneezes, how big are those droplets? How big should we expect them to be? So what happens when someone sneezes is initially they'll have liquid jets that emanate from their mouth, right? I'm sure many of you have seen videos about this at some point. That will have some velocity. So you can say or coughs. This will also apply. So have some velocity u, right? Both the direction and some magnitude. So now we have an idea. So we know these things have been studied. The speed of these are sort of well established. We know or can measure the speed. So we can estimate based on the surface tension and the density, which of these droplets, which are essentially water, what this droplet size will be. Or we at least can estimate it. So there are other things that we can understand too. From the Young equation, we can understand how long will these droplets last in air. Of course, you'd have to combine this with some mass transfer model that explains the different types of diffusion, convection, et cetera, that would be happening into the air. But we have an idea of the vapor pressure here, which is important. Okay, so this is something that I think is relevant now. I think that a lot of people are confused, for example, nowadays, based on some conversations I've had with neighbors or other random people when it comes to, for instance, wearing masks, how effective they are at holding back viruses, right? They correctly state that viruses are so small and they will pass through easily through the pores of a mask. And they are totally right if we were sneezing out pure virus particles, right? Viruses are on the order of a few, at the most, about 100 nanometers in diameter. And we aren't going to be spitting out virus particles. What we do spit out when we sneeze or cough are droplets that can contain virus particles. And you can estimate the size of these. And what you will find if you plug in numbers is they are on the level at which a filter system will catch them. The other thing you should probably know, at least from if you've taken separation processes, is that that even if things are smaller than a filter size, that they can be quite effective at catching particles. So for example, if you have a 200 micron filter, for example, and you're trying to, you have a droplet, for instance, that is, say, half that size, that does not, you can use similar relationships that what you've learned for membranes in the separation science class to understand how effective would, say, an N95 mask or even a cloth mask be at catching these type of droplets. So again, these are practical things that you can do back of the envelope calculations to convince your neighbor that, for example, wearing a mask is an effective way of mitigating the spread of disease. Okay, so you all have the tools to be able to do that now. Okay, so what else can we do? So we've done a couple different types of scaling limits. So let me do one more that involves one more dimensionless number. In this case, instead of inertia, let's scale the gravity. So let's scale this curvature force with gravity. Okay. So you can scale this surface tension force with the gravitational force. So this would apply to some falling droplet, for example. So suppose you have a cloud that's made out of water vapor and suspended liquid droplets. And it's raining. How large should these droplets be? And for simplicity right now, let's ignore drag force. Okay, suppose that instead of air atmosphere, we had a vacuum for now. Okay, so there is a relationship for this, and it is called the bond number. Let me pull this up really quick. So if you want to compare gravity to this curvature force, it's the bond number. Which we have as BO. This would be rho G A squared over the surface tension. So again, we can say that the balance between this will be when bond number is about 1, when those forces balance out. And we can then say that our characteristic length here will be the radius of our droplet. Which would be the square root of about what is this? Gamma over rho G. Again, an approximation. So if you were to take values for water at 25 degrees C, you would find that the water droplets would have a radius of something like 3 millimeters, approximately. Okay, so that's roughly, maybe water droplets are a bit smaller than that, but we're ignoring drag effects, which can both drag effects, which can further reduce the size both through breakup and by accelerated evaporation. But yeah, I think that that's something to keep in mind, that we can use the fact that we can, as engineers, we can scale different forces to get good estimates, right? So again, I'll put a caveat here. So notes ignores effects of drag and evaporation as it's falling. So we know that the evaporation that would occur also would not be primarily due to this Kelvin equation type effect. The vapor pressure would be roughly equivalent to the vapor pressure of a bulk liquid, considering that it's on the millimeter scale. But we do know that due to drag effects and enhanced mass transfer, because a large velocity that we have around this falling droplet, that there should be some significant evaporation effect that occurs because of that. So let's see, we have a few minutes. So what else can we talk about? So other things to think about, like one last thing that I want to think about is if we have a system. So suppose that we have, you're playing with bubbles, for instance, and you have a big bubble here and a small bubble here. So let's call this bubble 1 and bubble 2. And suppose you have a valve between these two and it's closed initially. So we have two soap bubbles attached to this apparatus. Okay. So suppose you open this valve. Which maybe let's frame it as, will the diameters of the bubbles change? Or which way would it change? Which way will air flow, right? So we have 2 minutes. So I want you all to, so you can do like emojis, right? And in this, so I want people to give me a thumbs up if you think that that bubble 1 will get bigger, and I think there's like this clap emoji. You can give me the clap emoji if you think that bubble 2 will get bigger. Let's see what the consensus of this class is. So I'm seeing a couple people. Yeah, so we have a mixed audience. I'd say roughly an equal amount of thumbs up and claps. All right, so this is a controversial problem, right? Which bubble is going to get bigger, right? Important stuff. So the first thing to think about is where flow. How does flow happen? Like flow happens from high pressure to low pressure. And our pressure, so our delta P, when we say delta P with reference to atmospheric pressure, is going to be, for a sphere, 2 gamma over R, right? So smaller radius means higher pressure. So that means that we're going to have flow, you know, when we open this valve in this direction. Okay, so we have flow from the small to the large. So this is the same thing that we had in the Ostwald ripening case a little bit ago. So the large bubble will consume the small bubble. You can do this experiment with, say, like a straw and bubbles if you're able to carefully stick two different size bubbles to a straw and see what happens. You will see that this does indeed occur. So if you have like a little brother, sister, niece, nephew, this will be a cool experiment. You'll probably trick them out a little bit. But we have like a second to end, but the end configuration will make sense. So this first bubble will be bigger, and the ending second bubble will have a spherical cap. So the spherical cap will have, let's call this R2. And if we consider not the radius, but the radius of curvature, for 1 will equal the radius of curvature for 2. So essentially this cap here will have the equivalent radius of an equivalent size bubble, right? That's what the radius of curvature will mean. Okay, so that would be the end configuration there. Okay, so yeah, we are just past the end of class, so let's end it there. We'll be talking about a couple other things based on the feedback that students gave in terms of what they wanted to learn most about for the next couple days. And starting next week, we'll be getting into presentations. So please use opportunities to get feedback from me for your projects if you need it. And otherwise, I will see you all on Wednesday.